We know how to determine the pH of strong acid solutions, right? They just dissociated 100%. There really weren't any calculations involved because, right, the acid dissociated 100%. And then we went on and we learned how to handle the pH of weak acid solutions. There we had to do ice to get the equilibrium concentrations of everything present. Now we're going to move on today to weak base solutions. So again, since it's weak, these solutions, these compounds, they're not going to dissociate 100%. So we're going to have to do ice again to get the pH of these weak base solutions. And we'll always get a pH less than 7 because they are weak bases. And like we said before, monitoring pH is a very useful thing in the environment or chemical processes, so this stuff is really applicable. For today's work, our weak bases are always going to come from this table. So here's their chemical formulas and their equilibrium constants. Okay, but notice there's a little subscript there, so we're going to have to write these base ionization reactions in a certain way. So these equilibrium constants, these Kb values, that are in the table, they're listed, but you have to write this hydrolysis reaction, right, the base in the table, reacting with water, you have to write them this way. Otherwise, right, these Kb values aren't any good. So you look up the base in the table, the other reactant's water, well, you get hydroxide, right, because it's a weak base, and then you get the conjugate acid. Of that weak base. So then how do you go ahead and write the equilibrium constant or the Kb expression? There's always products over reactants. So it would be the concentration of hydroxide, the concentration of the conjugate acid of that weak base, and then divided by the concentration of the weak base. And since water is a liquid, it doesn't show up. So we should have had a little L on here. We should have had AQs everywhere else because everything is solvated in water. Okay. Where do we get these equilibrium constant values? The table. So let's practice one. Let's write the hydrolysis reaction for ammonia and write its corresponding equilibrium constant expression. So ammonia is in the table. It's a weak base, so we can go ahead and write the weak base plus water. Okay, we can put subscripts on there, I guess. That would look better. Forms hydroxide and the conjugate acid. And you remember to get the conjugate acid, just add an H+. So that would be ammonium. And the Kb expression, products over reactants, hydroxide concentration, ammonium concentration, and ammonia concentration. Okay, let's try to find the pH and the hydroxide concentration of 0.01 molar pyridine. Okay, and this is from the table. So since this is a weak base, right, it's in the table, it's a weak base, and we want to know an equilibrium concentration, the hydroxide, we have to do ice. We have to do ice. But you do ice for a chemical equation. What's the chemical equation? Has to be the Kb chemical equation, the hydrolysis of pyridine. So how do you write it? Right, it's the weak base plus water forms hydroxide and the conjugate acid. Add an H+. H, C5, H5N plus. So our initial row, we have 0.01 molar pyridine, and water never shows up, so I'm going to put dashes all the way down. We don't have anything initial for hydroxide or its conjugate acid. The change row, minus x, x, and x. So equilibrium concentrations, 0.01 minus x for pyridine, x and x for the concentrations of the hydroxide and the conjugate acid. Next step, plug them into our Kb expression. And that number is 1.4 times 10 to the negative 9. That has to equal, right, hydroxide and the conjugate acid concentrations multiplied together divided by the pyridine concentration. Okay. Now remember that trick? Whenever we have 10 to the minus 4, right, when our K expressions are 10 to the minus 4 or smaller, we can do this. We can say that x is going to be very, very, very small. It's going to be so small that when you subtract it from 0.01, you essentially get 0.01 again. So on the bottom, we're going to have 0.01, because 0.01 minus x is essentially 0.01. We have x squared up on top. This whole thing equals 1.4 times 10 to the negative 9. Okay, solve for x squared, bring the 0.01 to the top, take the square root, and we'll get our answer. So 1.4 times 10 to the negative 9 times 0.01 equals, take the square root, about 3.74 times 10 to the negative 6. Okay, that's our x. So our x is our hydroxide concentration. Okay, and that's what they wanted. We should put units on it. Since the hydroxide concentration is 3.74 times 10 to the negative 6, the POH would be 5.42. Just take the log of it, right? Subtract that from 14, and your pH would be about 8.57. So there's our two answers. Find the hydroxide and the pH of this solution. So go ahead, do ice, set up the Kb expression, and solve for the hydroxide concentration. So the weak base plus water forms hydroxide and the conjugate acid. Make an ice table. The initial is 0.05. Water never shows up. Change, negative x for reactants, positive x for products. 0.05 minus x is my equilibrium concentration for my weak base. X and x are my equilibrium concentrations for the hydroxide and the conjugate acid. Set up my Kb expression. That's 4.7 times 10 to the negative 4. Products over reactants, x squared over 0.05 minus x. We're at 10 to the negative 4, so we can drop our negative x. So we can get our x. 4.7 times 10 to the negative 4 times 0.05. Take the square root. About 4.85 times 10 to the negative 3 is my X. And that's hydroxide. So let's find the pOH. The pOH is 2.31. So my pH, subtracted from 14, about 11.7, 11.68 or so. Separate 0.25 molar solutions of each of the following bases are prepared. Place a circle around the solution that will have the lowest pH, and a box around the solution that will have the highest pH. Okay, so all of these are bases in our table. So what's our game plan? Well, our game plan would be in our table, we've got all the Kb values. So just realize the bigger the Kb, then the more basic it is, right? The stronger the base. Then the stronger the base. So the one with the biggest Kb is going to be the strongest base. It will have the highest pH. Right? And the base with the lowest pH, that'll be the weakest. Right? That'll be the weakest, or the smallest Kb. Okay, so let's just list out our Kb's and you should be able to figure this out. So hydrazine, 1.7 times 10 to the negative 6. Ammonia, 1.8 times 10 to the negative 5. Ethylamine, 4.7 times 10 to the negative 4. And methylamine, 4.4 times 10 to the negative 4. So the largest Kb Let's try this one. If the pH of pyridine solution is 10.25, what is the concentration of the pyridine? And they give us the Kb number for pyridine. This is not an ice problem because they gave us pH. Right? They did not give us an initial amount of pyridine. They gave us the final pH. So we know the equilibrium concentration. Right? If we know pH, really we know pOH. And if we know pOH, we know the hydroxide. So let's just plug things into our Kb expression and see if we can see what we can get to work here. Our Kb, well, let's write our Kb reaction first. That might help. We have pyridine plus water, right? The hydrolysis of pyridine, Kb reaction, will form hydroxide and the conjugate acid. So my Kb expression, products over reactants, hydroxide, conjugate acid, all over concentration of the weak base, pyridine. Okay? So we know the concentration of hydroxide. So let's get it. If the pH is 10.5, the pOH is what? Subtract from 14. 14 minus 10.25 is about 3.75. So then my hydroxide concentration, remember, is just going to be 10 to the negative pOH. So that's going to be 3.75, make it negative, raise it to the 10 power power, about 1.78 times 10 to the negative 4 molar. There's my hydroxide concentration. So this is 1.78 times 10 to the negative 4. We know what Kb is. That's 1.4 times 10 to the negative 9. We're going to solve for the pyridine. All we need to know is what is the concentration of that conjugate acid? What is its concentration? Do you remember the trick to this? Pyridine, right, always the weak base breaks up into hydroxide and the conjugate acid. That's the hydrolysis reaction. They're always the same. They're always X and X. So our conjugate acid concentration is the same as the hydroxide concentration, 1.78 times 10 to the negative 4. So let's rewrite our expression here. We're going to have 1.4 times 10 to the negative 9 is going to be 1.78 times 10 to the negative 4. You could write squared, but we'll just write it twice. Divided by what we're trying to find, the pyridine concentration. So let's just kind of switch these two around. We'll have our answer. So we'll take 1.78 times 10 to the negative 4, square it, divide it by 1.4 times 10 to the negative 9. You get about 22.6. Will be my concentration of pyridine. So these problems aren't too bad. Just realize when you see one of these compounds, it's a weak base, so we need to write a Kb reaction and do ice because it's a weak system.